Hi everybody. So in today's lecture, I just want to talk a little bit about solutions. So I have two main goals for today's lecture. I want to review what you already know. So you may remember in the beginning of the year, we talked in fair detail about solutions and what they were and how they formed. So we're going to review some of those properties and characteristics. And then I want to talk about how we quantify solutions. So what do we mean when we talk about concentrations, and what are some different ways that chemists or other scientists measure concentrations of solution? Okay, so let's just review a little bit. So you may remember that solutions are homogeneous mixtures. So remember, homogeneous means the same. So they're homogeneous mixtures of two or more pure substances. So that means the substances disperse evenly throughout. And then we have two words that we use to describe this. So the solute is what's being dissolved, and the solvent is doing the dissolving. So if I were to add table salt to water, the table salt would dissolve. So the salt would be the solute, and it would dissolve in the water, which would be the solvent. Okay, and how does a solution form? Well, what's happening here, it depends on what these solute and solvents are. But in order for a solution to form, the solvent pulls the solute particles apart and surrounds, or what we say, solvates them. So there needs to be some attraction between this solute and the solvent. All right. And in chemistry, we talk a lot about ionic solids in water. So in our last unit, we talked about, for instance, those double displacement reactions. And we had to indicate whether it was aqueous or a solid. So if we were putting those AQ after our salt, then we meant that that was dissolving in water. In other words, those two ions were dissociating and being surrounded by water. Okay, so these solids dissolve to varying degrees, which is why sometimes in our product we would get a solid that would precipitate out of solution. But in general, when a soluble ionic solid is added to water, it interacts with the water molecules and dissociates into isolated ions that then diffuse out into solution. Although the strong ionic bonds in the solid are broken up, they are replaced by numerous favorable interactions between the charged ions and the partial charges on the appropriate ends of the polar water molecules. So let's see what that looks like. So do you remember how water what water looks like and how it interacts with itself? So remember, water is a polar molecule, which means that the charge is not distributed evenly. So in the case of water, the oxygen is going to attract those electrons a little bit more towards it. So you have this partial negative charge, and then the hydrogens get this partial positive charge. Right? It's not enough to transfer them. It's still a covalent bond, but remember, it's a polar covalent bond. All right, and so water then interacts with itself such that the partial negatives and the partial positives line up. And remember, we call this hydrogen bonding. So hydrogen bonds between water make water a very special type of solvent. Okay, and so because of these partial charges, water can also interact with ions that have a full charge, and they're going to do so in a similar way. So let's say we have sodium cations in solution. So the water pulled that sodium out of the crystal lattice and now is surrounding it because the partial negative charges of the oxygen align with the full positives of the sodium. And the same thing would happen to the negative chloride ion, except you'd have the hydrogen partial charges lining up. So this acts to pull that crystal lattice apart, and then once it's surrounded by water, it's not going to go back into that crystal lattice, and you have these sodium and chlorides distributed evenly and forming that solution. Okay, so what affects solubility? So there's three main factors. So the identities of the solute and the solvent. So you may remember we talked about like dissolving like. So polar molecules tend to be able to dissolve in other polar molecules, and nonpolar tend to dissolve in nonpolar solvents. So that's kind of like the first principle. And then you have to look a little further and ask things like how big they are and what those attractions are. But that's kind of the first rule to follow. And then we look at temperature. So as we increase temperature, we're going to increase the solubility. And then if we're talking about solutions that are made up of gases, we also can note what happens as pressure increases. Okay, so let's take a look in more detail at temperature. Okay, so you may have had the experience if you drink iced tea or maybe add sugar to lemonade and you stir it up that not all the sugar dissolves, right? It may be a little gritty or it may wind up in the bottom of the glass. So if you want to make a really fancy iced tea or a lemonade, you might make a simple syrup first. So in order to make a simple syrup, what you do is you take equal proportions of water and sugar. So let's say we have a cup of water and a cup of sugar. If this is at room temperature, I can dump the sugar in, and what's going to happen? Some of it's going to dissolve as you stir it up, but is all of it going to dissolve? Probably not. So you're going to wind up with a lot of sugar kind of mixed in with this water. So in order to get it to dissolve, what we do is we boil it to make our simple syrup. So as you increase the temperature of the water, more and more sugar is going to dissolve until eventually all of it's dissolved in the water. Okay, so do you remember these terms? All right, so saturated is how much of the sugar dissolves at a given temperature. And then when we boil this and dissolve more, and then we cool it off again, we now have a supersaturated solution. So there's actually more sugar dissolved in this than we would expect given the temperature, okay? And so this simple syrup then we can use to mix in our drinks, and then we don't have that gritty sugar, right? This is also how, if you've ever made things like rock candy, you make a supersaturated solution first, and then you add something to start it crystallizing, and it'll crystallize around, a popsicle stick, for instance, and you get that rock candy. Okay, so that's kind of a real world example of solutions and temperature. All right, so now what I want to do is talk about how we refer to solutions. So what do we mean when we think about the concentration of solutions? So a concentration in general is an amount per total volume. All right, so it's some amount per volume gives us the concentration. And so concentrations, once you have a concentration, you can pour off different amounts. The concentration will still stay the same because the amount per total volume is still the same, okay? So when we talk about concentrations in chemistry, we're going to talk about molarity, which I'll show you in a minute. But a concentration can be anything as long as it's some type of an amount. So is it something you weigh out? Is it grams per liter? Is it ounces per cup? Anything that's an amount per volume gives you a concentration. Okay, but in chemistry, we like to talk about molarity. So we spent a lot of time in the last unit talking about moles. So we're going a little bit back to moles. And we're talking about molarity, which is now moles of solution. So this is our amount. So remember, mole is Avogadro's number of molecules. So the mole of solute over the liters of solution. Okay, so it's mole per total volume, not just the solvent, but what you wind up with once you add everything. Okay, and in chemistry, this is the most common way. And you can talk about molarity. You can add those prefixes like millimolar or micromolar, and they work the same way as when we use prefixes in front of meter or liter or anything of that nature. Okay, so let's look at a few problems. Okay, so here we have what is the molarity, and molarity we designate with a capital M, of a 3.4 liter sample of a solution that contains 0.32 moles of sodium chloride. So remember, molarity is moles per liter. So we simply set up moles, so we have 0.32 moles, And our total solution is 3.4 liters. So 0.32 over 3.4, you divide through. So our molarity is 0.094 molar solution. Okay. And here's another question. So now we have to add one more step. So what is the molarity of a 0.5 liter sample of a solution that contains 0.45 grams of sodium chloride? Okay, so here we're given grams, but in order to get to molarity, remember molarity is moles per liter. So we go back, grams, we have to convert to moles, right? So you need the molar mass. So we can take 0.45 grams of sodium chloride, and the molar mass is 58.44. So moles over grams, we cross out the grams, and we get 7.7 times 10 to the minus 3 moles. And then we've got one more step. So we've got that many moles per half a liter. So moles per liter is molar. So our molarity is 0.015 molar. Okay. All right. So in chemistry, we also, or in biology and many sciences, you have to make up solutions. And so the directions will say, you know, make up a 0.9 molar solution of sodium carbonate. So you need to know how to do that. So what you do is you calculate the number of moles that you need, right? Use that to then convert to grams. You would weigh out how many grams you need, and then you fill the flask up maybe about halfway with solvent, swirl to dissolve, and then you finally carefully add enough so that you have the volume you're looking for. Okay, so let's see how that would work. So let's say we want to make a 0.154 molar solution of sodium chloride. And this is what we consider a standard saline solution. So this is basically the same concentration as what's in our bloodstream, for instance. So describe how you would prepare 1 liter. All right, so we know 0.15 molar. So the first thing we do is remember molar is moles per liter. Now we convert the moles per liter to grams. So again, we need our molar mass. The moles cross out. And we now know we need 9 grams per liter. And luckily, our problem just said 1 liter. So we're going to weigh out 9 grams. We're going to add water, we're going to swirl to dissolve it, and then we're going to bring it up to 1 liter. Okay? We're not going to work too much on these. We don't really have enough time, but I just wanted to make you familiar with some of the terms. And for those of you that go on in chemistry, you'll spend a lot more time with this. Okay, so those are kind of the main things in chemistry. You'll talk about molarity a lot, but there's a few other types of concentration that I just want you to recognize. So molality, and I don't know why chemists insist on using such similar terms, but molality is moles of solute per weight of solvent, so per kilogram of solvent. Okay, so it uses mass instead of volume. And so notice this isn't total solution anymore. It's solute to solvent. Okay. All right. And if you need to convert between molarity and molality, since you're converting an amount to a volume, you need to know the density. Okay. So if you're interested, you can look at this a little bit more closely. Percents is something we use in biology a lot. Anybody that's taking environmental next year, we'll talk about percents. They can be weight per weight. So percent means per 100. So it's going to be mass of A over the total mass times 100. Or you can have weight per volume, which would be grams per mil times 100. Okay. And then finally, you can also have things like parts per million or parts per billion. Again, we'll encounter this a little bit in environmental. This is a little bit older terminology. So marine biology, you may use parts per billion and parts per million and parts per thousand. Again, concentration can be any amount as long as it's an amount per volume. Okay, so I hope you learned something, and I'll see you next time.